this video on static timing analysis. So in this video we will be doing hold time analysis. So this is the circuit. This is the first flip flop. It is called as the launch flip flop. This is the second flip flop. It is called as the capture flip flop. So this flip flop is called as launch flip flop because it will launch the data D1. This D1 data will be produced at the output. It will travel through this combination logic. Then it will be produced at the input of the second flip flop. This second flip flop will capture this data and produce the output. That is why this is called as the launch flip flop, because it launches the data, and this is called as capture flip flop because it captures the data. So we will have two important parameters. One is the setup time, second is the hold time. So what is the setup time? So setup time is the minimum amount of time for which the data must be stable before the arrival of the clock edge. So suppose this is the clock edge. Suppose this is the clock edge. So the setup time is the minimum amount of time for which the data must be stable before the arrival of the clock edge. So let's suppose this clock edge is arriving at 15 nanosecond, and let's suppose the setup time is 3 nanosecond. So the data must be stable after this 12 nanosecond because the setup time is 3 nanosecond. So the data must be stable in this part, which means the data must not be changing. This is called as the setup time. Then the hold time. The hold time is the minimum amount of time after the arrival of the clock edge for which the data must be stable. Let's suppose the hold time is 2 nanosecond. So the data must be stable till 17 nanosecond because the hold time is 2 nanosecond. So this is called as the hold time, and this is called as the setup time. So the setup time is the minimum amount of time before the arrival of the clock edge for which the data must be stable, and the hold time is the minimum amount of time after the arrival of the clock edge for which the data must be stable. So the hold time is denoted by TH and setup time is denoted by TSU. So here we have considered that setup time is 3 nanosecond and hold time is 2 nanosecond. So the data must be stable in this period from 12 nanosecond to 17 nanosecond. So this is the basics of the setup time and the hold time. Now, so during the setup analysis, so in the setup analysis, we have to ensure that the data which is launched by the launch clock at the current clock edge must be stable at the input of the capture flip flop at least setup time before the next clock edge. So again I am repeating, in the setup analysis we have to ensure that the data which is launched by the launch flip flop at the current clock edge must be stable to be captured by the capture flip flop at least setup time before the next clock edge. So this is the next clock edge, this is the current clock edge. So for the setup time analysis we consider that this data which is launched by the launch flip flop must be stable at least setup time before the arrival of the next clock edge. Then it will be captured by the captured flip flop without any distortion. And during the hold time analysis, what we have to ensure is that the data which is launched by the launch flip flop at the current clock edge should not travel to the capture flip flop before the hold time has passed after the clock edge. So because if the hold time has passed, then it will guarantee that the data which is captured by the capture flip-flop will not be corrupted with the next data. So if suppose capture flip-flop is capturing this data D2, then this data D1 should not corrupt this data D2. So that is why what we want is that the data which is launched by the launch flip-flop at the current clock edge should not travel to the capture flip-flop or should not arrive at the capture flip-flop before the hold time has passed at the clock edge. So the capture flip-flop can capture the data. So we will take some cases to understand it. So the first case is TC2Q equal to 0. Second, and in the same case we will also consider that the clock skew is equal to 0 but the hold time is not equal to 0. This is the first case. So TC2Q, it means the amount of time taken by this launch flip-flop for the data to be produced at the output. Then this clock skew is equal to 0. It means this clock signal arrives at both the flip-flop at the same time. Then this hold time is not equal to 0. So we are considering that we have the hold time which is not equal to 0, and we are doing the hold time analysis first. We are not doing the setup time analysis here. So when the rising edge arrives, then this launch flip-flop will launch this data immediately because this TC2Q equal to 0. Now this data will travel through this combinational logic. So it will arrive at the capture flip-flop at time tcom. Let's suppose the delay through the combinational logic is denoted by tcom. So this data will arrive at the capture flip-flop at the time tcom. So this tcom must be greater than the hold time. Otherwise this data D1 will corrupt this data D2. So this is the required condition for the hold time to not be violated. Okay, otherwise if T combinational is less than T hold, then this data will arrive at this capture flip-flop before the hold time has passed. So the hold time will be violated. Now consider this second case. In the second case, clock to Q delay is not equal to 0. So this will take a finite time to produce the output. The clock skew is also not equal to 0 and the hold time is also not equal to 0. So suppose the clock edge arrives at t equal to 0. The clock edge arrives at t equal to 0. Then what will be the data arrival time? So what will be the data arrival time? So when the clock edge arrives at t equal to 0, then it will take tc2q time to appear at the output. This data will take tc2q time to appear at the output. Then it will take the t combinational time to appear at this d2 input. Okay, so and we have considered that the clock skew data is not equal to 0. So let's suppose the clock will take time delta 1 to arrive at this launch flip-flop. So if the clock edge is at t equal to 0, then it will arrive to this launch flip-flop at delta 1 time. Then it will take tc2q time to arrive at the output. Then it will take t combinational time to arrive at this point. So data arrival time will be equal to delta 1 plus tc2q plus this combinational logic delay tcom. So this is the data arrival time. Now we will calculate the data required time. Now we will see the data required time. So this clock signal has arrived at t equal to 0. It will arrive to this capture flip-flop at time delta 2, where delta 2 is the clock skew at the second flip-flop. So the data required time will be delta 2. And we have considered that the hold time is not equal to 0. So the data required time is del 2 plus th. So this is the data required time. Because this capture flip flop will start capturing the data and won't accept any new data for at least hold time after the arrival of the clock. So this clock signal is arriving at time delta 2. Then this capture flip flop will take at least hold time th to capture the for the data to be stable after the arrival of the clock edge. So this is the data required time. We require this time for the data to be arrived. So for no hold violation, the data arrival time must be greater than the data required time arrived. Otherwise, if the data arrives at before this time, then there will be hold violation. So the data arrival time must be greater than the data required time. So we can write the equation like this: delta 1 plus T C2Q plus T combinational must be greater than delta 2 plus TH. So this is the equation for no hold violation. This is the equation for no hold violation. Okay, if this equation is not satisfied, then there will be hold violation. So the data arrival time must be greater than the required time. If the data arrival time is greater than the data required time, then it guarantees that the data which is captured by the capture flip flop is not corrupted by new data. So again, let us, if we take the clock skew to be delta 2 minus delta 1, then we can write like this also: TC2Q plus Tcomb must be greater than clock skew delta plus TH, where delta clock skew is equal to delta 2 minus delta 1. So this is the equation for no hold violation. So in the next video we will be doing some numerical on this concept. Thank you. Please like and share the video and subscribe the channel for more such videos on static timing analysis.